Hello from Lake of the Ozarks. My name is Robert Daniels. This is my Intro to Data Science final project. The goal of this project was to see if we could predict outside temperature based on frequency of cricket chirps. The challenge, the professor gave us a sample data set. We were to perform exploratory data analysis on that data set, sanitize it if needed, use that sanitized data to build a linear regression model on the KNIME platform, and then test that model for reliability. So the dataset itself, as provided, was a raw CSV file with 58 records. The official shape was 59.2, as that includes the attribute labels. The attributes in this case were chirps, chirp frequency per 15 seconds as measured, and temperature in degrees Fahrenheit. Initial checks, you can kind of see that there are float values, and we found that there were 2 null values per attribute. So the null value is pretty messy, right? A computer probably doesn't know how to handle null explicitly. It probably shouldn't even guess because there's really not, it requires some level of discretion in terms of what you want to do. Data are expensive most of the time, and you don't want to just throw out every single record that has a null value. Let's say you have like a 12-dimension data frame. You don't want to throw out the full record just because it's missing one piece of one dimension. That's very expensive, and I don't want to be the person to tell the manager that you're throwing out that much data. In this case, though, we actually only have 2 records that have a null value. It's not really in this slide at the moment that each one of these attributes with 1 null that happens to be in different records. So we have 2 records that are compromised. In this case, 2 records out of the full 58 means we can safely drop those 2 records and not lose much out of the data set. After we've dropped that using the drop NA functionality of Python Pandas, we have the 57 non-null rows. Keep in mind again that it does include the attribute column, so we have 56 records that we're going to be looking at. The technical issue of the null being fixed, now we're going on to the statistical issue of outliers. Outliers, by definition, are not the norm. They are outside of regular parameters. For whatever reason, they do not fit in with the rest of the data set, and if we do include them, we're going to be skewing our data. It's relatively easy to see as plotted using the box plot functionality of Pandas. This is a screenshot taken from a Jupyter Notebook. You can visually see right here when you render the box plot that, hey, there are outliers involved. Same thing over here on Seaborn. You can kind of get a grasp of how much it would be skewing the magnitude of the data set just from looking at how smushed, I guess I can use that term there, just how everything else is kind of skewed downwards because these outliers are being taken into effect. So what do we do about these outliers? Well, first we need to figure out, okay, how many outliers do we have? Same thing applies from null values. We don't want to throw out half the data set, which, I mean, kind of by definition, if half the data set's an outlier, you got more problems. But first, let's find the outliers. So to do that, I converted each of the attributes into a NumPy array. I took a splice of the chirps column and a splice of the temperature column and converted it to a horizontal 1D NumPy array. Used the function to find the the third quartile, first quartile, and from that you could find the interquartile range, Q3 minus Q1. And in this case, I went ahead and just used the quantile functionality method of NumPy, giving it the parameters array, the arguments array, and 0.75 and 0.25. At the end of it, it will console log out the outliers for chirps array, which is what is in the screenshot here. The outlier was 361. There was also an outlier in the temperature set, if you recall. It's not in this screenshot. So we only have 2 outliers out of the data set of 56 now. That still is a pretty acceptable loss to just drop those 2. There are many different ways of dropping those outliers. Some are much more sophisticated than just chopping off at the below 361 and chopping off below 6 and below 361. What we got here is just a quick mask to the data frame itself. The data frame is now everything with chirps below 361. The data frame is now everything with temperature above 6. This then leads to a much cleaner graph to then look at. You'll notice that the magnitude of this is not skewed anymore. Everything is falling between the min-max values. We have the median. There's no outliers outside of the box and whisker plot. Down here, you'll see the Seaborn data set, which is much cleaner, much more one-to-one strong correlation relationship. For the actual paper, the NIME scatter matrix is what was turned in. This is the same functionality. We can kind of see just visually that there does appear to be a striking relationship between chirps to temperature. And so now that we have the clean data set, we can keep moving on from there. The general statistics of these data, we have median listed at 50%, 29.5. The first quartile, third quartile, min-max. Means also available pretty easily. You'll notice it's very simple, a single line to pull these data out. I don't want to calculate that by hand. I don't think I should calculate that by hand. Kind of moving through, these are the same data points that are used to render that box plot that we saw on the previous slides. So we have a general idea of the statistics. We also have relatively clean data set, and we have a visual rough estimate that, hey, there is a strong correlation. This is a good time after we've invested some resources into this to see, okay, is it still worth it to continue this analysis? So our goal, to recall, was to see if there was a strong correlation between chirp frequency and temperature. I think the official terminology we used is, can we predict temperature based off chirp frequency? But this is just a more formal statistical statement of that question. We found a visualization that said, hey, yeah, it looks like there's a strong straight line between chirps to temperature. And based off of those observations, we can say, okay, it's probably worth it to keep moving on with this analysis. Don't chase good money after bad money. If after you're doing the original analysis, you see just a very fuzzy data set and there doesn't seem to be much relationship, don't continue dumping money into this unless there is going to be a pretty high reward for it. To continue to then move on to actually build our model, we will use NIME. So what is NIME? NIME is a data analysis platform that is available for use that can integrate data, process data, use models, spit out machine learning results, and you can kind of use this to get a grasp of what you're wanting to answer. So in this case, we're trying to answer, hey, is there a linear relationship between chirps and temperature? Linear regression is a supervised learning method, which means that we have a known data set that we think should be a linear relationship. We're going to tell the computer, hey, please look at these data and build a model off of these data. And then after it gives us back the model, in this case, a line of best fit, we're going to use that line of best fit equation with a new data point and see what that model would predict. So the NIME workflow, in this case, we need to import the data into the platform to a form it can read. Using CSV Reader, that's how we did that. We can run basic statistics using linear correlation, and same thing down here, we can actually run a scatter matrix, which is the NIME version of the Seaborn scatter plot. The actual line of best fit is from the linear regression learner application. So what comes out of that? First, we look at the correlation measure. The correlation value in this case is found to be 0.9802, which is a very strong correlation value. This correlation value will move from -1, perfect negative correlation, to +1 to perfect positive correlation. If we get a value at 0.980, that's a pretty good indication that's a very, very strong correlation. It definitely is not indicative of causation, but that's an entirely different statistical method here. So in this case, again, we have 0.98. That means, hey, strong correlation, we're going to see a good, solid fit. So running it through, the main deliverable of a linear regression model is the line of best fit. The line of best fit, I believe would be on, we'll go ahead and kind of go over the line of best fit in just a second, but it's kind of to see, here's what we were told in NIME. We were told chirps has coefficient 0.892 and the intercept is 40.025. What does that mean? That is a regression line. The regression line is the line of best fit. It is a straight line. If you remember from algebra, y is equal to mx plus b in this case. M is the slope, b is where the line will intercept the y-axis. So if you look back, what NIME told us is that, hey, the slope of that line is going to be 0.892 chirps, and the intercept of that line will intercept at 40.025. So if you take temperature, which is the Dependent variable in this case is a function of chirps. And if you take that multiplied by 8.92 multiplied by the chirps, which is the independent variable, add 40.025, that will give you your number. So let's go ahead and try it. We were given the line of best fit in here, which actually sorry about that, kind of jumped around a bit. That line of best fit, the official definition, you should pretty much consider it is if you take every single point of the data set that you have and you take the vertical distance from a line, the theoretical line that's drawn, and you sum all those up after you have squared each one to get rid of the negative value, you'll get a number. And this equation, y equals mx plus b, is a very simple equation that has to be run many, many, many times because it needs to be ran against each individual data point. And thankfully, computers are very good at that. I am not. I would go crazy if I had to do that by hand. But let's say that takes a theoretical permutation and it says, okay, if I take the distance from this point to the line, that point to the line, square it, and then sum all those up, that's going to give us, for sake of argument, 29. And then it tries the next one, and that one gives us, for sake of argument, like 54. Discard the 54, keep the equation that gives you 29. 29 is new minimum. Keep repeating that until you get a minimum value for all these items, and then return that line as a line of best fit. So we have our deliverable, y equals mx plus b. Let's see what happens if we say, hey, I just recorded 40 chirps. What should the temperature be based off of that? So if you plug in basic algebra in here, 40 into the chirps value, and solve for temperature, predicted temperature would be 75.705 degrees Fahrenheit. Great, we have a number. It's not the temperature of the sun, which is good. It's also not 0 degrees Kelvin, which is also good. So it is within physical reason. At the same time, though, we do need to check for reasonableness. Even if you're very sure of your model, you should always use some common sense and be like, okay, does this return something that I could be okay presenting to my manager or be okay presenting to the client? So at 40 chirps, we'd expect 75.7. Let's go back to our known data set of what actually happened, sort by chirps. We're going here, 40 chirps between 37.8 and 43, 75.7. You could see that. That's a reasonable number to pull from. This isn't a hard number. This isn't like a mathematical proof. It's just using some common sense. Okay, 40 chirps at 75.7 would fit nicely into this data set. So we've met the reasonableness requirement. Continue again. Interpretation at this point, we have a strong correlation. We have a model that has produced a reasonable result. We have a reasonable basis now to conclude that we can predict outside temperature based on chirp frequency. This doesn't disprove the null hypothesis, nor does it prove our hypothesis. It's just saying there is a strong correlation. We should be able to predict that based off of the data that we've just discussed. So the next steps. This is a very small data set. In theory, if you're going to want to actually sell this product, you're going to probably want to gather more data to make sure this isn't a fluke. With such a small data set, any small variation is going to have an outsized influence on the end result. You should also check for confounding factors. You can imagine there's so many things that would affect an insect. Humidity, weather, time of day, if it's in the morning, if it's in the night. Do crickets chirp more in the morning, or is it too dangerous to chirp in the morning because of predators? I truly do not know. I'm not an expert in crickets, never claimed to be. More importantly, explore business use cases. Is it cheaper to measure cricket chirps or more accurate to measure cricket chirps as opposed to just pulling out a $2 thermometer? Almost certainly not. Probably get laughed out of the room if you try to sell this as the actual deliverable. The data scientist, in theory, is paid well for their work, right? But in return, you're going to have to probably give them something that has an ROI, right? Like it's an investment. They've invested resources the company has. You need to make sure either academic results or business results, you need to give an ROI. My gut instinct in this case, even though we treated the chirps as the independent variable and temperature as dependent variable, it actually works, it's opposite in real life, right? Like if we somehow trained crickets to chirp slower or chirp faster, we're not going to change the ambient temperature of the environment. It'd probably be a pretty wild set of circumstances if that was the case. It's almost certainly the other way around where temperature is affecting cricket chirps. So you could kind of imagine if somehow we determined that insects chirp um, more or less based on if they're stressed or if they're hungry or if there's like a population density problem. You would imagine that, hey, it's very cheap to go out and measure the temperature, and then you can measure cricket chirps and see if it is above or below tolerance of the model. And based off of that, you can probably see, okay, is the insect population distressed in some way? We can't go and ask a cricket how it's doing if it's hungry or whatnot. We have to kind of look at things that could be gathered efficiently. This may be a very efficient way to gather those data. So to recap, we had our initial question, can we estimate outside temperature based on chirp frequency? Our initial data read showed there were some technical issues in terms of the presence of null values, some records were missing data, and there's also statistical outliers present. We did scrub both of those out of the data set. We removed null values, discarded outliers because they were such a small portion of the data set. The clean data was then fed into KNIME, the linear regression learner, to try and find a line of best fit. It did give us a line of best fit that we then validated against a new data point, and that new data point did come in as a reasonable measure of temperature. And based off of all these observations, we came to the conclusion, correlation, not causation, based off the data, ambient temperature can be estimated based off of chirp frequency.